In this video, we're going to talk about differentials. So remember when we first started our calculus, we would have a function here, f of x, and then we would set up 2 points, a and b, and then we would say the average gradient that exists between a and b would be given by the height here, which is delta y, divided by the across here, which is delta x here. And then so this here is the average gradient. To get the true gradient, we would need to decrease this delta x here. We would need to take the limit as delta x tends to 0. So this here is the average gradient. This here is the average gradient that exists between a and b. But then to get the true gradient, we would need to apply the concept of limits to take us to dy by dx here. So this thing here becomes this, and then this thing here, well, another way of writing it would be f prime of x here. So from here we can get to here. Now here's the thing. Hang on. This here is the average gradient. This is the average gradient. Apply the concept of limits. That will then take us to dy by dx. So when you think of dy by dx here, you have to gear your mind into thinking on a microscopic scale, because don't forget, looking at this here, delta x here is the across distance here. Delta x, when delta x represents a small change in x, so delta you can think of it as being a small change in, and then in this case small change in x. So when you're talking about delta x, you may be talking about on a scale of let's say 0.0003 here. Okay, so on this delta x scale, you may be talking about 0.0003, and then when you're here, once you've applied the concept of limits here, and then it becomes dx. Now on a scale of dx, on a scale of dx here, when you get to this dy by dx, you have to gear your mind into thinking on a microscopic amount, because on a microscopic scale, because from here you've applied the concept of limits. So you've applied the concept of limits. So you have to think, when you get to dy by dx, you have to gear your mind into thinking on a microscopic scale, because delta x here, when you are here, delta x here, you may be talking about on a scale of 0.0003. But then when you get to delta x here, when you get to dx here, this 0.003 is still too big. When you get to delta x here, you are probably talking about on a scale of on this scale here, 0.0000000000003 here. Maybe this. So hang on. What I'm trying to say is that on this scale here, delta x here, this is quite realistic here, this amount here. But once you've applied the concept of limits, then it becomes dx here. But then this dx here, you have to gear your mind onto thinking, into thinking that it's on this scale here, and maybe this scale here is still too big. Maybe you have to even go smaller. The point I'm trying to make is that this delta x here, this is your average gradient. Once you've applied the concept of limits, you will get to dy by dx. But when you get to dy by dx, gear your mind into thinking on a microscopic scale, because you've already applied the concept of limits here. So hang on. So when you get to this scale, when you get to this here, normally once we know the gradient of a particular point, if you know this distance here, you can just get this distance and then times the gradient. That will then give you this height here. But remember, once you know, if you know the gradient at this particular point, if you times the across here, that will then take you that will then give you your height here in a way. But then after you've applied the concept of limits, you need to gear your mind into thinking on a microscopic scale here. So when you get to this thing here, this thing here is too big. You have to zoom in even further into somewhere around here. So the point is that the point is that you can, if you want to know the up and down here, this thing here, dy here, if you want to know the up and down here, you can just get dx times the gradient at this point here. So that would, so if you want to know the up and down here, which is, let's just say dy here. If you want to know the up and down here, you can actually say dy is, well, just get the gradient at that point, and then times dx here, and then you can say it's equal to, because we've already applied the concept of limits. So we've just zoomed in so we've zoomed in so far that well, on a microscopic scale, you can actually say dy by dx equals the gradient times the across here times dx here. But don't forget, this dx is on a microscopic scale. It's so small. You can actually say that this equals, definitely equals, this whole thing here. Okay. The point I'm trying to make is that you when you're after you've applied the concept of limits, you would get to dy by dx here. Once you're on this scale here, gear your mind into thinking on a microscopic scale, and then this is your up and down here, and then this here is your cross here. But if you want to know the up and down here, you can just times, well, if you want to know the up and down, you can get the gradient and then times the across here. Okay. The point I'm trying to make is that you can treat this as one thing. You can treat this as one thing. So this thing here represents the across. This thing here represents the up and down here. And then the up and down here, is equal to the gradient. Well, if you know the gradient, you can just times it by the across here. So the point I'm trying to make is that after you've applied the concept of limits, you can treat this as like one whole thing and one whole thing here. You can times both sides by this. So gear your mind into thinking on a microscopic scale once you get to dy by dx, and then the differential of y, which is this dy here, the differential of y is equal to this times dx. Don't worry if you don't understand this. I will give you I will guide you further in the next video. Okay.